Hello, we are Michał Kucharczyk and Jacek Rutkowski, and we would like to talk to you about our final project, Riemannian HydrAMP. We are in quite a good position because there was already one presentation about HydrAMP, but I will make a short recap because some of you came later. So HydrAMP is a model destined for antimicrobial peptides generation. Antimicrobial peptides, that is some biological entities which might be crucial in some 30 years for medical applications. And in the architecture of this model is based on variational autoencoders. But there emerged some problems with this approach, with these simple variational autoencoders, and they are somehow stated here. Okay, so we have these two antimicrobial peptides, cefaxin and OP145, and we have already trained variational autoencoder. And there is a parameter tau, which says how far from the encoded representation of antimicrobial peptide we go in the latent space. And here we have the number of generated candidates around this antimicrobial peptide. So as we can see, for cefaxin, there is much less of generated candidates than for OP145. So we might ask, why is that so? Why there is much more generated candidates for OP145 than for cefaxin? And the answer is that around OP145, the latent space is more dense, so to say. The density here is much bigger. So we have here a map of the Earth, and if cefaxin is at the center of the map, the unit is quite small. Okay, and here at the boundaries of the map, in the Middle East, one unit is very big. So if we take one step in this map around OP145 in the Middle East, we go very much. While where we go one step from cefaxin, we go much smaller distance. So if we treat this latent space simply as Euclidean space, the problem like this emerged. That is the problem that we have less candidates for those points in the latent space for which the space is somehow less dense. Okay, so how could we solve this problem? We have decoder from this latent space. Decoder is a neural network. Neural network is differentiable by design. So maybe we will use differential geometry. Differential geometry, which allows us to somehow take into account the distortions of the latent space. We do not treat this latent space as simply Euclidean space, but we want to take into account these distortions. So using this decoder function from the latent space, we can define Riemannian metric in the latent space, and grace to this approach, we can treat these points somehow equally. This cefaxin and OP145. We equip this latent space with some meaningful metric, with some meaningful distances. So what we have done in our project is that we computed distances in this latent space equipped with this Riemannian metric, and we also visualized half lines in this latent space. So there are several packages for Python which want to solve some problems of differential geometry and which aim to visualize the latent space, to visualize some differential geometry objects, but they were not satisfactory. It was impossible to put there some model and like a variational autoencoder and visualized the latent space. So we have done some work to solve this.
Okay, so what we did, we created a Python package and we called it latent geometry. And what it basically does is it allows a user to provide some function, having in mind, for example, a decoder in variational autoencoding setup. And here's an example usage. So you just need to create some simple net, for example. It can be in PyTorch, TensorFlow, or some other framework. And after you have that, you just need to pick a metric for the ambient space, how we want to measure changes in the space that is understandable for us. For example, with HydrAMP, we have peptides in the ambient space, so we need to design some metric there. But usually we can just pick Euclidean metric. And once you have that, that's the only thing you need to provide. And you can ask this manifold. You can pick 2 points in the latent space and ask for a line that the shortest path between two, with respect to the metric that you provided for the ambient space. So what we basically do, we take the metric from the ambient space and put it in the latent space, and we can walk there. And the second thing we can do is we can pick 1 point and another direction, and we want to go straight in some direction. And here's a simple visualization. So we use this function as an input. It has 2 variables, x and y, and z is some function which is like hilly, as you see on that picture. And if we wanted straight lines if we treated latent, here is a latent space. If we treated like a usual Euclidean space, then we would have just straight lines. But if we want to represent them as a straight lines in the ambient space, as you see here, then they go uphill and they twist, and that's a visualization in 2D in the latent space. So that's a typical, let's say, usage. Okay, so we want to take this package and use it for the HydrAMP, but we encountered some problems. Namely, the HydrAMP was written in old TensorFlow, which was not as differentiable as we would like to. It is connected with some architectural designs that were made there. It is not that interesting. The other thing is that the computations are slow because we need to solve some differential equations using SciPy, for example, and it takes time. And so we did not done that yet. It's a work in progress for a master thesis. But what we did is we took a simple variational autoencoder with 2D latent space, and we trained it on MNIST. And it's this is the latent space of this MNIST. And then what we did is we, just as on the first slide, on the second slide, we wanted to create the straight lines and then draw circles, but using the proper metric for latent space. And as we see, this space is twisted. And so that's a visualization of what we wanted to achieve with this package. And yeah, that seemed to work here. And yeah, next steps is to, as we mentioned, just tackle the problems we had with HydrAMP. So we will probably rewrite HydrAMP in the newest version of TensorFlow or PyTorch and retrain it, and then do some optimization so that we can, achieve all of what we want in a reasonable time. Yeah, and that's what I will do in my master thesis. And I believe that's it. Thank you.
Okay, let's thank the speakers.